Hello and welcome back to Introductory Astronomy. The last chapter introduced you to the gas and dust between the stars that are raw material for new stars. Today, we will start putting together observations and theories to learn how nature makes stars from the interstellar medium. The stars themselves are not eternal. When we look at the sky, we see hundreds of points of light, and amazingly enough, each one, just like the sun, is a tremendous nuclear fusion reactor held together by its own gravity. The stars we see tonight are the same stars our parents, grandparents, and great-grandparents saw. Stars don't change perceptibly in a person's lifetime, even during all of human history, but they do not last forever. Stars are born and stars die. And this chapter is going to start us along the story of star formation. Here in this picture, it is a visible infrared combined image, which was captured with the new wide-field camera on the Hubble Space Telescope. And we see a highly detailed view of the largest stellar nursery in our local galactic neighborhood. It is called R136, and it is located about 170,000 light-years away. This region is about 100 light-years across, and it harbors a rich collection of hundreds of young blue stars amid reddish gaseous nebulosity abundant in hydrogen from which they formed. And this probably happened as recently as a few million years ago. In this chapter, we're going to talk about the star-forming regions, how stars like our sun have formed, and then we're going to move on to stars of other masses. We're going to talk about cloud fragments and protostars, shock waves, and in general star formation. And we're going to start talking a little bit about star clusters. Now, astronomers find hundreds of places in the sky where clouds of gas glow brightly because they're illuminated by the hottest, most massive, and luminous stars, which are spectral types O and B. These kinds of stars pour out such floods of energy that they can last only a few million years. So we must be seeing them pretty near where they were born. O and B stars are therefore signposts pointing to star-forming regions, which are always among the densest parts of the interstellar medium. The giant star-forming region at the right, called NGC 604, is roughly 500 parsecs across. It is found in the nearby galaxy M33, displayed at the left, on the much larger scale of 40,000 parsecs across. As we saw in the previous chapter, spectra of the interstellar medium, the ISM, show that its chemical composition is basically the same as stars. By observing at far infrared and radio wavelengths, to which interstellar dust is basically transparent, we can peer inside even dense molecular clouds and find evidence that stars are forming there. Star formation happens when part of a dust cloud begins to contract under its own gravitational force, as shown in frame A. As it collapses, the center becomes hotter and hotter until nuclear fusion begins in the core. Now, when we're looking at just a few atoms, the gravitational force is nowhere near strong enough to overcome the random thermal motion. But when you have enough material, then we can have a collapse taking place that can eventually lead to star formation. In these frames over here, we see the motions of a few atoms within an interstellar cloud and how they're influenced by gravity. In frame A, we can clearly see that the atoms are strongly influenced by the force of gravity. In frame C, we see pretty much an accidental random encounter. So no gravitational collapse in that case. Now, when the dust cloud is beginning to collapse, not everything necessarily goes according to plan. There are some things that are resisting this gravitational collapse, and they can interfere with that. Two things that are very important that are fighting this gravitational collapse are rotation and magnetisms. Let's start with magnetism. The interstellar medium is filled with a magnetic field. Now, this field is only about 0.0001 times as strong as the Earth's magnetic field, but it is enough to act as an internal spring and prevent the gas from contracting. Neutral atoms and molecules are unaffected by a magnetic field, but ions having an electric charge cannot move freely through a magnetic field. Although the gas in a molecular cloud is mostly neutral, some ions are included, and that means a magnetic field can exert a force on the gas as a whole. Gravity must overcome the interstellar magnetic field to make the gas contract. Under some conditions, the ionized gas in giant molecular clouds can gradually recombine with free electrons. The resulting less ionized gas is freer to slip past the magnetic field and contract. This process has been observed inside isolated molecular clouds. And the thing about rotation, everything in the universe rotates. As a gas cloud begins to contract, it spins more and more rapidly as it conserves angular momentum, just as ice skaters spin faster as they pull in their arms. This rotation can become so rapid that it resists further contraction of the cloud. Now, stars go through a number of stages in the process of forming from an interstellar cloud. I like this table right here because it's a very nice summary of the pre-stellar evolution of a solar-type star. And as you can see, this evolutionary process has been divided into 7 stages. Stage 1 corresponds to the interstellar cloud. The approximate time from stage 1 to stage 2 is 2 million years. The central temperature of the interstellar cloud, as well as its surface temperature, are about 10 degrees Kelvin. The central density is 10 to the 9 particles per meter cubed, so 1 billion particles per meter cubed. And the diameter of the interstellar cloud is about 10 to the 14 kilometers, which is very, very, very large. As you go through this table, you see that all the stages, we start from the interstellar cloud. The cloud begins to fragment because of the influence of gravity. It turns into a protostar. Eventually, the protostar will turn into an actual star, which will get to the main sequence. And you can see through in column 2 how long it takes to go from each stage to the next. And you see this is a very long process. And as this takes place, as the interstellar cloud contracts more and more and more, notice how the temperature is increasing. So we're starting from an interstellar cloud of only 10 degrees Kelvin, and we go all the way to a 15 million Kelvin main sequence star. And of course, since all that material contracted into a smaller and smaller diameter, it means the density must also have increased, which is why we start with a density of 10 to the 9 and we get to a density of 10 to the 32 as the diameter of the cloud is decreasing and decreasing. So let's take a look at the stages one by one. Stage 1. We have our interstellar cloud that's floating out in space, and it starts to contract. It was probably triggered by some kind of pressure wave or a shock wave from a nearby star or a nearby cluster of stars. As it contracts, the cloud fragments into smaller and smaller pieces. This slide right here depicts its cloud fragmentation. So as the interstellar cloud contracts, gravitational instabilities cause it to fragment into smaller pieces. Now these pieces themselves continue to fall inward and fragment further, eventually forming many tens or hundreds of individual stars. Stage 2. Individual cloud fragments begin to collapse. Once the density is high enough, there is no further fragmentation. Stage 3. The interior of the fragment has begun heating and it now reaches about 10,000 Kelvin. Remember, it started at 10 Kelvin. Stage 4. The core of the cloud is now what we call a protostar, and it starts to make its first appearance on the HR diagram. What is a protostar? Astronomers define a protostar as a pre-stellar object that is compressed enough that it is opaque at all wavelengths, but not so hot and compressed as to be able to generate energy by nuclear fusion, as would a main sequence star. Instead, a protostar shines with energy released gravitationally from a combination of matter falling inward to the protostar, plus slow contraction of the protostar itself. If we take a look at the familiar HR diagram, we get to see a protostar. The red arrow on the upper right indicates the approximate evolutionary track, followed by an interstellar cloud fragment before reaching the end of the Kelvin-Helmholtz contraction phase as a stage 4 protostar. The boldface numbers on this and subsequent HR plots refer to the prestellar evolutionary stages listed in Table 19.1, which are also described in the text. So if you go back to slide 6, you can compare the numbered stages that follow with the temperatures, the densities, the diameters of all these objects that correspond to the prestellar evolution. Now, planetary formation has begun, but the protostar itself is still not in equilibrium. All heating comes from the gravitational collapse at this point. So if you take a look at this artist's conception of the evolutionary stage, we see that in stage 1, we have the interstellar cloud, and about 2 million years later, we move on to stage 2 fragment, a smaller, hotter stage 4 fragment with jets, and finally a stage 5 protostar. Now the duration in years is a lot, so this is a very, very long process. The last stages can be followed on the HR diagram. So once we get to stage 4 or so, we have the protostar. And the protostar's luminosity, as you can see from the HR diagram, is decreasing as it's going through stages 5 and 6. But notice how, as its luminosity is decreasing, its temperature is rising. Why is that? Why do you guys think that's taking place? Because the object itself is becoming more compact. So as things get more and more dense, more compactly put together, their temperature is rising. Okay. Stages 4 to stage 6 are actually given the name Hayashi track. Stage 7 itself is at the point where the newborn star has arrived on the main sequence. Once it gets on the main sequence, it's going to stay there until it runs out of nuclear material to fuse. Looking at stage 6, we're at the point where the core has reached 10 million Kelvin, and that's the minimum temperature for nuclear fusion to begin. So that is our definition for a star. The star is going to continue to contract and increase in temperature since it's getting denser and denser until it reaches an equilibrium. That equilibrium stage is stage 7. And that is the main sequence stage. And again, the star will stay on the main sequence as long as it has hydrogen to fuse. Now, what if you have stars that have different masses than the sun? They're different. They're either more massive or less massive than the sun. This HR diagram here shows the evolution of stars that are more and less massive than the sun. As you can see, the shape of the paths is very similar. What is different is that they wind up in different places on the main sequence. And as you can see, a star that is 3 times the mass of the sun is going to be located on a higher position on the main sequence, whereas a star that is 3/10 the mass of the sun is going to start its life on the main sequence at a lower point. Now, you know that the main sequence is kind of this curvy band that we can put the stars on there, and like we said before, about 90% of all the stars lie in the main sequence. Now, this main sequence is not a straight line, and that's because stars of the same mass can have different compositions. So that's why it's a curvy band. But something that's very important I want to make sure I point out is that once a star gets on the main sequence, that's it. It's going to stay there until it finishes fusing hydrogen. It will not move along the main sequence and move across it. Once a star reaches the main sequence, it means it is in equilibrium, and it will not move up or down, left or right. It's not going to do anything until its fuel begins to run out. Now, our sun has been on the main sequence for 5 billion years on that same position, and it's going to remain there for 5 billion years more, because that's how long it takes to fuse the hydrogen that our sun has in its core. Now, some fragments are too small for fusion ever to begin. What happens to those fragments? They will never end up becoming stars, and they gradually cool off and become dark clinkers. A protostar must have 0.08 or 8% the mass of the sun in order to become dense and hot enough that fusion will eventually begin. And 8% the mass of the sun corresponds to about 80 times the mass of Jupiter. If the mass of this quote-unquote failed star is about 12 Jupiter masses or more, it is then luminous when it's first formed, and it is called a brown dwarf. This covers sections 19.1 through 19.3 in your textbook. At this point, you should be able to summarize the sequence of events leading to the formation of a star like our sun. And you should be able to explain how the formation of a star depends on its mass, and how they're going to end up on a different part of the main sequence band based on their mass. Until next time.